approximations to roots. And sometimes that's the best we're going to do, because some equations are just too hard to solve. I mean, if I said to you, solve e to the power of x is equal to 5x, that's just too hard. So we come up with techniques that allow us to get a pretty good approximation. The first one is quite logical. You'll see what I mean. It makes perfect sense. It's called halving the interval. Because you see, what we know is this. If we've got a function, let's just draw a function. It's continuous, so there's no breaks into it. And what I know is that somewhere between A and B, there exists a solution. And I know that because function A here, you'll see, has a positive number, and function B is a negative number. And if it's continuous, well, you can't get from positive to negative without going through 0. So the solution must be there somewhere. And the question is where? And as I say, logic says, well, halfway. Let's estimate halfway. Now, when using this sort of method, or any of the approximation methods, the key is the continuity. Because if I was to say use the hyperbola as an example over there, and I was to look at function 1, oh, it's positive. Function negative 1, oh, that's negative. I can't draw the conclusion, oh, there is a solution to 1 on x equals 0 between those two, because it's not continuous. So if you ever get a question which says explain why, it's continuity is the key. So don't just say, oh, well, I know function A is positive, I know function B is negative, therefore there must be a solution. It's and the curve is continuous, therefore there's a solution. So all right, let's find a solution. We know there is a solution somewhere between 1 and 3 for this particular equation. Okay, so there's our function. Function 1 turns out to be negative 16, function 3 positive 68. So, okay, I'll estimate it at 2. I wonder if 2 works. Well, let's see. Oh, no. It's not a solution. Function 2 is 1. But what I can now say is, well, hang on a sec. I know that function 2 is positive. So I can halve the interval again. But obviously the interval I'm going to choose is not between 2 and 3, because they're both positive. I'll choose the interval 1 and 2. So let's try 1.5. I mean, you've got to lie somewhere between 1 and 2. Average it, 1.5, sub in. Oh, that was a good move. Negative 10.9. Heaps closer. Maybe. But what it actually does do is go, okay, well, look, now I know that the solution must exist somewhere between 1.5 and 2. Oh, let's average it. 1.75. Oh, negative 6.12. All right. Well, that therefore means logically there must be a solution between 1.75 and 2. Let's average them. But I think this question just set to 2 decimal places, didn't it? Yeah, so there's no point carrying more than 2 decimal places. My estimate will be 1.88. Oh, minus 2.75. Okay, let's try this. We now know that the solution must lie in between 1.88 and 2. Let's average it. 1.94. Negative 0.96. All right. Well, now I know my solution is in between 1.94 and 2. We'll find the average of 1.94 and 2. 1.97. Oh, that's class. 0.001. But now we know the solution is somewhere in between 1.94 and 1.97. So the average is 1.96. Minus. Okay. But now I know the solution is in between 1.96 and 1.97. Well, which is it closer to? Because to 2 decimal places, if I round off, the answer is going to either be 1.96 or 1.97.
Just do one more anyway.
Yeah, but how could I tell which one is going to be closer to?
If it's negative. Yeah, if it's negative, you can bring that in. Bring that one.
In the middle of which one? Yeah.
Halfway is 1.965. Now I will carry that extra decimal place.
Oh.
This is where it'll be useful. Function 1.965 is negative 0.16. Therefore, the solution is in between minus 1.965 and 1.97. Now, every number that's in between 1.965 and 1.97 will round to 2 decimal places to be 1.97. So whatever that solution happens to be, I go to 2 decimal places, it'll be 1.97. Yep. So I just keep halving it and halving it and halving it until I know the definite interval that it's going to be, and then I'll go one more decimal place to see which end is it closer to. That took quite a few goes, you may have noticed. It would have been a little bit quicker, but anyway. Good old Newton does so many things for us. What a guy. He came up with a method of approximation which was quite clever. Huh? However, it all comes down to our first approximation being a good approximation. Because what it ends up doing, let's draw the curve in, is it actually finds where the tangent cuts the x-axis. So if my first approximation there is x naught, what it's basically doing is finding the equation of the tangent and where it cuts. And that x-intercept becomes the next approximation. Because theoretically, depending on how steep the curve is, it should get closer to that point if I've got a good first approximation. Yeah? Now obviously, up here, if my first approximation turns out to be a stationary point, the method's going to fail altogether because it'll never cut the x-axis. So that's not a good approximation. That's what we call a pathetic approximation. That's the technical term. All right. We're going to derive the formula here. How can I find this x-intercept? Well, the slope of the tangents will be, there's a point there that I know. Its x value is x naught. Its y value would be function x naught. And a second point on this green line is x1, 0. So I don't actually have to go and differentiate the curve here. I can just find the slope of this straight line. So the slope of that, function x naught minus naught on x naught minus x1. So the derivative is equal to that at x naught because the derivative is the slope. If I was to rewrite this by multiplying by the x naught minus x1 and then dividing by the f dash x naught, we come up with a formula because remember we're trying to find x1. So x1 will end up being our first approximation, x naught, minus function x naught over the derivative of x naught. Now, the big mistake people make is putting the derivative on the top instead of the bottom. How do we remember this? Well, remember it fails if we have a horizontal line which is a slope of 0, and you can't have 0 on the bottom of the fraction. So that's a way of remembering. And you can keep going and find more approximations. So to generalise it, xn plus 1, you get the one before it, xn minus function xn over f dash xn. Let's do the same question and see how good Newton's works. So function x to the 4 plus 2x minus 19, we're going to need the derivative, 4x cubed plus 2. Now we're going to need a good first approximation. Don't say 1.97. We're going to need a good first approximation.
2.
2? Well, we know there's a solution between, what was it? So 2 would be a logical one, so that's why I picked 1.5. Yeah, you're right, 2 would have been logical. But anyway, 1.5 is my first approximation. So there's function 1.5. There it is when I sub it into the derivative. Bung it into our formula. We get 2.21. Now, how good is my next approximation? No. All right. Try again. Well, derivative 45.1754. Bung it into the formula. 2.00. Maybe I should have picked 2 straight away, hey. But anyway, we're there now. Function 2 is 1. Its derivative is 35. Sub it in the formula, 1.97. Okay, remember we don't know that's the answer yet because we're pretending we didn't do the other bit. Okay, how's 1.97? Ooh, wow, that's pretty close, 0.001. What's its derivative? 32.58. Now right now should give you a clue that it's going to be good. Because look, the numerator of the fraction is like 0.001. The denominator, 32, I mean, we're adding a very small number. Oh, to 2 decimal places, it's 1.97. Same answer. So 1.97 would appear to be our better approximation. Let's go back to this question. So what we need to do is come up with an equation that we know the answer to this equation is the square root of 23. So x squared minus 23 would be a solution. So the derivative is just 2x. I'm going to create a general formula by subbing in these straight away. So my formula is going to be x to the n equals x to the n minus 1 minus x to the n minus 1 squared minus 23 2x n minus 1. Oh, look, I even tidied that up by getting the common denominator. That was fancy. I'm going to use 5 because I know the square root of 25 is 5. So it seems a logical place to start because I reckon it's going to be closer to 5 than 4 because it's obviously 16 versus 25. So if I sub in 5, 4.8. 4.8. Okay. Sub in 4.8. 2.7958333333333333. But to 2 decimal places, that's 4.8. So it looks like 4.80 is our answer. So some other problems with Newton's method. Oscillation. Look at this idea. So here's our random curve. Just say I want to find that particular solution. And I decide there's my first one. Okay, so x2 is going to be my next approximation. So from there I'll draw in the tangent and x1 will be my next approximation. So if you're really unlucky, you might get something like that, where it just oscillates between a couple of solutions. Yeah, exactly. So you just need to move one of those approximations a bit closer and you should be okay. Wrong side of the stationary point. So say I wanted to find that one, but I decided I'd pick there. Now it'll find an approximation, but not to the solution I'm looking for. It's finding one of the other solutions. So that could be a problem. Ooh, there we go. Look, only a handful of questions there to do.